Hello. Today we're going to talk about dependence and correlation. Remember earlier I mentioned that statistics can be difficult for students, partly because the concepts all have many different vocabulary words. And many of these vocabulary words are different from words that we would use in everyday conversation. So for example, we talk about the mean of a set of samples. Really, we're talking about the average. It's just another word that means that has the same synonym, has the same interpretation. So we are going to introduce a couple of new words here, but once again, we're going to take it nice and slow, and we're going to use real-world demonstration of how statistics really works. Mostly, it's just counting things and adding them up and then finding their average and things like that. It's all things that you already understand from daily life, but I do need to put it in sort of statistical terminology because that's important to understand when you're reading a report regarding statistical analysis or you're writing a report yourself. That kind of terminology helps explain things a little bit more precisely than if we just go ahead and try and paraphrase or use synonyms. So let's go ahead and take a look at two important terms, dependence and correlation. So up until now, we've done what we call independent analysis. So that means we really only analyzed one random variable or one value. So a random variable is, in this case, let's say the length of a randomly selected potato. Now, if it was a normal kind of a math variable, like x, then you might say, well, x plus 3 equals 5. Solve for x. Oh, x must equal 2, because 2 plus 3 equals 5. So that's the normal kind of a algebra variable. A random variable really says that the length of the potato is dependent on, which potato you randomly picked out of our sample. So we call that a random variable, but otherwise it works just like any other variable. But we talk about statistical truths about that variable instead of absolute truths. In other words, we say that it's most likely the answer is this value, or the distribution of the possible answers looks like this kind of a shape. So we really only concerned ourselves with this univariate analysis up till now. In other words, only one of the values varied, and that was the length of the potato. And so we went ahead and determined things like mean and median and mode of that random variable. We also found the probability distribution, or in other words, which potato lengths were more likely to come out if you randomly picked a potato from the sample. And we drew a histogram chart of that. And then we used that histogram chart to determine various likelihoods, like how likely is it that you would get a potato length that is less than 4.7 inches, things like that. And we talked about the confidence intervals. That likelihood is sort of our confidence that we'll pick a potato that is shorter than that length. So let me go ahead and review these same concepts I just spoke out loud, but we'll do it with pictures that you'll probably recognize from the earlier videos. So let's take a look at our independent analysis. We said that we had a bunch of potatoes. We just looked at one of the variables, the length of the potato, and we found out a lot of important information about our sample set. So we found out the total range, what's the maximum length and the minimum length of all the potatoes that we measured. We also found the mean, otherwise known as the average length, by adding up all the lengths and dividing by the number of potatoes that we had. And we also found the median, the length of a potato that would chop the sample in half, such that half of the potatoes in the sample would be shorter than the median and half of the potatoes in the sample would be longer. We also grouped potato lengths into equal-sized bins. So in this case, each bin was about a third of an inch from minimum to maximum. So you can see the bins on the left-hand side of the slide. The first bin all the way at the top is anywhere from 3.2 inches up to 3.5 inches, or the bin size is 0.3 inches. The next bin, which seems to have a lot more potatoes in it, is also 0.3 inches in size. It goes from 3.5 inches up to 3.8 inches, and et cetera, et cetera. So what we're doing is we're counting how many potatoes from our sample were in each bin. And we create a histogram, which is a bar chart, where the the length of the bar represents how many potatoes we found that were within that range of sizes for that particular bin. But the histogram also represents what we call the probability distribution of potato length. So that's a statistical word that just means, how are these potatoes distributed over those different bins? And we can see which lengths are more probable or more likely to occur in our sample set because the histogram bars are bigger. Turning that histogram chart on its side, now we could have a case where every single potato was equally likely to fall in one of these bins. We would say that all the histogram bars were the same height if each of the possible bin lengths were equally likely. Another common probability distribution is the Gaussian or the normal or the bell curve. Those are all synonyms for the same kind of a bell-shaped curve that has one peak in the middle and kind of drifts off to zero on either side. But in our case, the sample results in this kind of a lumpy probability distribution where there's a couple of peaks, and that's the ranges of potato lengths and how many potatoes fall into those ranges. So that's pretty much a review of our independent analysis of when we were looking only at one independent random variable. It's just the length of the potato. So we can use that information from the histogram to create these confidence intervals. So for example, we're 87.5% confident that if you close your eyes and randomly select a potato from the bag, our sample, it would be somewhere between 3.2 inches all the way on the left and 4.7 inches almost all the way to the right. So basically the first 5 histogram bars, but not counting that 6th one. And we do that by counting. We actually counted the number of potatoes that fall within that 3.2 inches to 4.7 inch range, and we divide that by the total number of potatoes, and that's how we came up with this confidence level, this percentage likelihood, this probability. So that's really how we deal with random variables. It's not like x plus 2 equals 5, oh, the answer is 3. When the length of a potato is a random variable, we can't say for certain what the length of the potato will be when you pick it out of the bag, but we can make some certain statistical likelihood or confidence interval statements about, what are the chances that you'll get a potato within a certain range of lengths. So let's move forwards and talk about the idea of an event. So I'm going to use the word event to mean, something an experiment that we go ahead and perform, or something that we do with the statistical values. So let's talk about that confidence interval as if it were an event, and we'll call that event A. So we can define that experiment or event A to be some event where a person picks a random potato from the sample, then that person measures its length, and then that person finds out that the length is somewhere between 3.2 and 4.7 inches. So therefore, we will say that if we define that experiment and we say that that's event A, is that you picked a potato and indeed it did fall within that range, we can therefore say that the probability of event A is 87.5%. Same as we said in the previous slide, but now we're just giving it a new name. We're calling it event A. But it's the same meaning. We're just giving some rules about the experiment we're going to perform and the likelihood that the experiment will be successful, that we actually do pick a potato that's between those lengths, is 87.5%. And we can write that using the shorthand notation P parentheses A end parentheses equals 87.5%. You can see it on the slide there. The P stands for the probability, and the event, the A, is in parentheses, so it's the probability that event A will happen. That's 87.5%. So that's kind of how statistical or statisticians talk about random variables like the length of a potato. They talk about different events, and then they give them probabilities based on mostly counting, adding them up. So a statistical analysis can determine the likelihood of one event happening, but also based on the fact that another event is also happening. So this is called dependence, because the second event depends on the first event. Now, if there's no dependence, then we say the two events are statistically independent. So we can go ahead and say that the likelihood that your car will sell for a value greater than $10,000 seems to depend on how many years old the car is. So as the car gets older and older, it seems to change the likelihood that your car will be able to sell for more than $10,000. And that's pretty much how we talk about a dependent variable. But let's say that you're sitting in the car and you roll a pair of dice and you add up what the values of the dice roll is. That has no dependence on how old a car you're sitting in. So the year of the car there's no dependence between you rolling a dice sitting in the car and the year that the car was built. There's no dependence there. They're completely independent. You rolling the dice has no correlation. We use the other word correlation. No correlation to how many years old the car is. It doesn't matter how many years old the car is. You're going to roll the dice. It's going to come up with a number. Dice have nothing to do with the car that you're sitting in. So we talk about dependence when two variables might depend on one another. Let's take a look at that in action. So here is our Excel spreadsheet where all the potatoes are listed, and then we sorted the potatoes by length, or that first column all the way on the left-hand side. So to the right of each of those lengths is the corresponding width of that same potato. So remember, when you sort by one value, make sure you select all of the columns that you want sorted. Otherwise, you'll start to scramble and confuse lengths with widths. I need to have the length and the width of that particular potato, always together. I don't want to scramble and throw away our good data that we took all that time to measure. So just remember, when you're doing the sorting, make sure you sort all the columns, but based on the value in one of the columns. Just a side note there. But once again, here's our spreadsheet where the potatoes are sorted by length, and to the right of each length is the corresponding width of that very same potato. So let's define a new event, and we'll call that event B. And that will be when the width of the potato is greater than 2 inches. And you can see a few of them in that second column. You can see a few potatoes that have a width that is greater than 2 inches. By going down the width column and looking at it closely, we can see that our sample set actually contains 8 potatoes out of those 24 that have a width that is greater than 2 inches. So out of a total of 24 potatoes, 8 divided by 24 is 0.33333333. And we go ahead and use the percent to mean multiplied by 100. So we write 33.3%. So the probability of event B happening is 33.3%. It's the probability that you'll randomly pick a potato out of the bag that is greater than 2 inches in width is about a third of the time, 33.33333%. So let's go ahead and see dependence in action. So I've colored in yellow all the potatoes that have a width that are greater than 2 inches. There's 8 of them. And we learned earlier that probability of event A, that the potato's length is somewhere between 3.2 inches and 4.7 inches. That had a probability of 87.5%. And the probability of event B, that the width is greater than 2 inches, is 33.33%. So the above are basically called independent probabilities, since there's only one event in parentheses after the letter P. The letter P stands for probability. What if we want to calculate the probability that a potato falls between 3.2 and 4.7 inches, assuming that that same potato has greater than 2 inches in width, event B? So we write this as a probability with a P, and then in parentheses, the A with a vertical bar, and that's on your keyboard, it's the shift key, and then that backslash is usually a vertical bar above that. Maybe it looks like it has 2 dashes on your keyboard, but it's just basically a vertical bar. And then the letter B, and then the end parentheses. So when we read that aloud, that P parentheses A vertical bar B end parentheses, we read it aloud as the probability of A given B. So what does that mean? That means that what is the likelihood of event A given that we already know event B has taken place? The probability of event A given the fact that event B is taking place. So that vertical bar, that's the dependence part. So we're looking for the dependent probability of an event A taking place given that we know event B has taken place. Let's go ahead and take a look at that with just counting. Remember I said all of statistics can be performed by simply counting how many of them there are. So as usual, finding probabilities involves counting things. So there are 8 potatoes that fall into event B, and those are colored in yellow. And that's really where the width of that potato is greater than 2 inches. So we're really only looking at those 8 potatoes. We're no longer looking at all of the potatoes in the bag. We're only concerning ourselves with those that have met the event B criteria, and that is that their width is greater than 2 inches. So within that group, there are 6 potatoes that also qualify as event A, and those are colored in dark green. So the length is between 3.2 and 4.7 inches. So counting, again, 6 out of those 8 yellow boxes, 8 yellow rows, I should say, because it represents the whole row. 6 out of those 8 event Bs are also event As. Therefore, the probability of A given B, that's how you read aloud P parentheses A vertical bar B end parentheses, right? The probability of A given B is 6 out of 8, or 0.75, or 75%. So that's a different probability than just the probability of A. So the probability of A given B is 75%. It's a different probability than just the probability of A. So one thing I wanted to note in terms of how statisticians write things, if I put a bar over the letter or an apostrophe after it, it means not A. So an event A did not happen. So the probability of not A given B is 2 out of 8, or 25%. So you can count them and you can see if you get the same answer there. I just wanted to make that side notation there. So dependence isn't always such an obvious thing. One of the things that statisticians learned is Bayes' theorem. So Bayes' theorem states that it's a complicated equation, but I'll go ahead and read it aloud for you. The probability of A given B is equal to the probability of B given A multiplied by the probability of A all divided by the probability of B. So that seems kind of weird, but there are proofs for that, and I'll leave that for your own research to go ahead and take a look at how that's proved. But it all has to do with counting things. So the proof has to do with literally counting how many of these events take place. So in words, what probability of A given B, is equal to this formula. Let's see if it holds true for our sample data. Let's go ahead and calculate these things. So Bayes' theorem says that formula, probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. So we have most of the values we already need to test the formula. We already know that the probability of A, just independently, is 87.5%, and the probability of B independently is 33.3%. And also we earlier calculated the probability of A given B was 75%. All that's left for us to figure out is the probability of B given A, and then we can work out our formula and see if it comes true. So to find the probability of B given A, guess what? We're going to count some things. So first we count all the events A, and then those are the ones that are in green. Those are 21 of them that are between the length of 3.2 inches and 4.7 inches. So then we want to see within that group how many of them also are satisfying event B. And those are in a darker color green. That's where those potatoes from event A are also, their width is greater than 2 inches. So what we do is to calculate the probability of B given A. I see that there's 6 of them in dark green out of those 21, all the greens. And so that's equal to 28.57%. So let's see if Bayes' theorem is true for our bag of potatoes. It's saying that 75%, or the probability of A given B, is equal to 28.57%, which is the probability of B given A, multiplied by the probability of A, which is 87.5%, and then the whole thing gets divided by the probability of B, which is 33 1/3%. Guess what? It does equal 75%. Bayes' theorem holds true. So if you're interested in artificial intelligence or software that looks for patterns, especially dependencies, you should look into Bayes' theorem a little bit more. So artificial intelligence or pattern analysis, things that look for those kind of dependencies, like predicting the path of a rainstorm or determining the model of a car shown in a picture. These are all based on Bayes' theorem, Bayes' analysis, Bayes' theorem analysis. We'll go into that in a different lecture. It's not really needed for the report that you're working on right now. But putting that aside, let's talk about correlation. So we said when things are dependent, then their statistics vary because if we know one fact, we can understand the probability of another event. So we can quantify how much dependence there is using that correlation number. And what we do is we calculate the correlation between two events. We can also visually view that correlation and therefore dependence with a scatter graph. So let's take a look at both of those things using your Excel spreadsheet. So here I've come up with some fake numbers, nothing to do with potatoes. I just put some numbers down. And I called event B, and it has a bunch of different values, actually just counting 1 through 9. And another event, A, that is not correlated to event B. In other words, I just went ahead and put some random numbers there, also between 1 and 9, but you can see that they're kind of scrambled and pretty darn random. So when we use the Excel function correlate, or C-O-R-R-E-L parentheses, that's in Microsoft Excel, you'll be asked to choose which two columns of data or which two groups of data you want to see if they're correlated or not. So when I type in equals C-O-R-R-E-L begin parentheses, then I can select all the values in event B, put a comma in there, and select all the values of that second column, the not correlated column, and we can go ahead and calculate that correlation. So a correlation, you can see, is calculated on the bottom row of that Excel spreadsheet, and it's 0.0769. It's practically zero. It's a zero correlation between those two numbers because event B was clearly getting bigger and bigger, and the other not correlated event is just kind of random and scrambled. In other words, the probability of A, or the not correlated, given B, event B, is nearly the same as the probability of A. In other words, the probability of getting different values for event A has very little to do with the values of event B. So we would say that A is not correlated to B. Rolling the dice in the car has nothing to do with the year the car was built. You're going to get values rolling the dice that are completely independent, are not correlated to the year of the car that was built. Whereas if you're trying to sell the car and you're looking at the dollar value and whether or not you get more than $10,000, that would be correlated to the year the car was built. And the probability of you getting more than 10,000 of all the cars in the world would be different than if you selected only cars that are recent model cars that have been built in the last couple of years. So if I were to plot these using a scatter plot, in other words, I select both columns and then I go into the Insert tab of Microsoft Excel and I insert a scatter plot. It's one of the different plots you can select. So the vertical axis has the values that event B showed up with, the kind of scrambled up values. And the vertical and the horizontal axis, it says vertical here on the slide, sorry about that. The horizontal axis, that has the values of, backwards. The horizontal axis has the values of event B. You can see it goes from 0 to 9. And then the vertical axis has the random, crazy scrambled up values of event A. So you can see that the values of A jump around. Sometimes they go up, sometimes they go down, going left to right. It doesn't seem to show any kind of uphill or downhill pattern. So that's typical of a non-correlated two different events that are just not correlated. They go ahead and two different random variables that do not have a correlation with each other. They go ahead and look kind of random and scrambled. Let's take a look at a positive correlation. So here, once again, event B has values 1 through 9. But now the positively correlated event in the second column has, crazy values, 101, 209, 306. But you can see that they tend to go up as event B goes up. Not exactly, not a straight line, but, kind of a bumpy line. But if I go ahead and use that CORREL, or the correlation function in Excel, it practically equals a 1. It's like 0.9999, etc. So these two events are extremely correlated, and they're correlated in a positive way, so that the numbers in event B, as those numbers go up, so do the numbers of event A. So you can clearly see the uphill trend in that scatter plot that I also show below there. Positively correlated random variables will have that trend towards either an uphill. When one of the numbers goes up, the other one also goes up, and we would say that they're positively correlated. These are definitely strongly correlated. It's practically a 1, strongly positively correlated. We can also have a strong correlation, but it can be negative. So in other words, for example, as the car gets older, the price goes down. So as the number of years ago you bought the car goes up, the price, the resale value of the car goes down. So we call that negatively correlated. And here we just picked some numbers, put in that negatively correlated column. And we see that column B, as column B goes up, those negatively correlated numbers go down. Not exactly, they're not 9 through 1, but they're different values. But they are definitely correlated. When you look at the scatter plot, you can see a definite kind of a downhill tendency. So if I get a number that's very close to a 1 in the correlation, we would say it's positively correlated. If I get a number that's very close to -1, then we would say it's negatively correlated. And if I get a number that's close to 0, we would say there's no correlation at all. It's just they don't have anything to do with each other, these two random variables. Now, it is a gray area where we say, well, exactly when would you say that they are connected to each other? Usually statisticians look for something greater than a 0.7 or less than a -0.7 to start saying, yeah, we're starting to see a strong correlation here. 0.7 would be a strong correlation. But if we have values that are kind of 0.5, it's not really 0, but it's also not really a 1, then we start to question ourselves and say, are these really correlated, or am I just looking at the random effects of the particular sample that I chose, the particular bag of potatoes that I chose? So here we see that we have a correlation that's a very weak correlation. It's 0.3 for these potatoes. They're weakly correlated. So I would not go ahead and say that there's a strong correlation. It's not really close to a 1. But also I wouldn't say that they're completely independent. It's not really a 0 there. So correlation, when it calculated, falls, remember that it always falls between -1 and 1 when you calculate that value. The closer the correlation is to the middle, or basically closer to a 0, the less correlated the two events are. And here we see that there's, some correlation of potato widths to lengths. It's a positive number. So as the length goes up, the width does, tend to go up, but it's not really a strong correlation like the other one we saw where it had a positive 0.99. So I guess we can see that there's some correlation between the width and the length of the potato, but it's a weak correlation. So that's really what we have to look at, and maybe we might propose further research into this data because we're really not sure of our hypothesis, but I wouldn't go ahead and say that we've strongly proven our hypothesis. Remember, our original hypothesis was that as potatoes get longer, they also definitely get wider. But here you can see all the potatoes have been measured, and sometimes the one potato is longer than another, but it's also skinnier than that other one. So it's not really a really strong correlation. Usually, like I said earlier, if it's greater than 0.7 or less than -0.7, if you will, then we would say that there's a strong correlation. But that's not true for this group of potatoes here. The scatter graph of the potato lengths, which are the x-axis or the horizontal axis, and the potato width, which is the y-axis or the vertical axis, also shows, there is sort of an uphill trend, but honestly it's not a clear line. It's definitely more of a cloud. And yes, the right-hand side of the cloud is a little bit higher than the left-hand side of the cloud, but that's not true for every point on that. And that's kind of how a lot of the data that we're going to be looking at in the real world, works out. It's always, if we could go ahead and make these strong correlations, we would be able to definitely predict, a lot of things like the stock market or the weather. But as you quite know clearly from your day-to-day life, it's pretty tough to pick the stock market every time, and it's pretty tough to predict the weather with any distance into the future. So correlation is usually the kind of thing that we definitely look for, but don't always find. As another visual representation that I like is when I graph the potatoes both length and width on the same chart. Remember, I already sorted the potatoes by length, and I made sure that both of the columns were selected when I did the sorting, so that these 2 points represent the same potato, and these 2 points, they're from the same potato because I sorted them, at the same time. So we go ahead and we graph both of them on the same chart. So you can see here that the lengths are definitely going uphill because that's the way I sorted them. But the widths are not really going uphill. They only sort of generally a little bit go uphill. But there's plenty of bumps along the way, narrow potatoes, wide potatoes, all along the path there. So that's just another way of visualizing the correlation or how much the width of the potato depends, the dependence on the length, or the correlation between the potato width and length. So hopefully in kind of natural language, regular everyday talk, I've helped you understand statistics and a couple of important values that you'll be using in your career going forwards. You do need to understand statistics. We also kind of dipped our toe into some of these pattern analysis and machine intelligence, artificial intelligence algorithms that are mostly searching huge amounts of data for these kind of correlations, these kind of dependencies. And now you understand why it's so critical to go ahead and understand these correlations or understand these dependencies when you're doing very difficult, complicated things like trying to recognize someone's face from a photo, trying to predict the weather several days in advance, trying to predict which direction the stock market will go. These are all very difficult problems that involve lots of data from a lot of different data points. But we kind of dipped our toe in it by using some real world examples, just everyday bag of potatoes, and we measured their lengths and widths, and we came up with a theory or a hypothesis that as potatoes get longer, they also definitely get wider. And we were able to put some statistical measurement on our theory, on our hypothesis, to see whether or not, really the probability of the width going up, is it or is it not correlated or dependent upon the length of the potato going up. So I'm going to leave you to analyze your particular bag of potatoes and do that analysis on your own. And I really want to thank you for taking the time to listen to this video as well as the other videos in the series. Good luck to you and enjoy.